Welcome to the Design for Test Fundamentals course. I'm Vinita Nelson. I'm an AE and an instructor here at Cadence. Let's get started. Take a few moments to read through the module objectives. Today we want to go over the very basics of testing digital ICs. We assume that you have some familiarity with the high-level chip design process and the place of test within the flow. There are no labs for this course. This is the agenda for the course. We're looking at some of the basic questions about test, which are, why do we test, what do we test for, how do we generate tests, and when did all this happen? First, we'll look at what chip manufacturing test accomplishes within the overall chip design process. Chip design is a process of reducing the levels of abstraction from a very general description to the masks that control the chip manufacturing process. Each time the level of abstraction is reduced, there is a transformation of the current state of the design to a new state. Some form of verification is performed to ensure that each transformation was performed correctly. It is the concatenation of these transformations and their verification that allows us to invest the amount of time that it takes to manufacture a chip. For example, a graphics chip design would start its life cycle with something as simple as this statement. I want a graphics chip that shows me a realistic view of an arbitrary three-dimensional world without any image flicker or jerkiness. That's pretty abstract. So how does it get turned into a chip? That very general and abstract description is reduced through a series of steps like these to millions and millions of rectangles. Those are then combined to create the masks that control the chip manufacturing process. This is sometimes referred to as the analysis or synthesis cycle of engineering. The problem is analyzed to break it down into successively simpler problems until the solution of each is clearly understood. Those many solutions are then put back together to synthesize the total solution. This cycle is repeated one or more times at each level shown here, but it's also the character of the overall process. At each step, one or more verification steps, such as one shown on the right column, are used to ensure that the transformations are correct. As a side note, the two columns are not intended to line up. Early on, assertion and transaction checking may be used. As the design progresses, various simulations are used. Later, automated transformations such as synthesis, place and route, formal verification, and timing verification come into play. During mask generation, shapes checking and optical inspection techniques are used to ensure that the technology ground rules have been followed. Finally, the manufactured chips are tested both before and after packaging. The chip manufacturing testing is a verification of all of the steps from the gate-level netlist to the manufactured chip. For a design that has moved from a hardware description language through gate-level transistor-level netlist to shapes and finally silicon, manufacturing test compares the behavior of the gate-level netlist to the observed behavior of the manufactured silicon. An important point to keep in mind here is that the chip functionality is complete by the time the gate-level netlist is complete. Therefore, manufacturing test tells you only that the chip was manufactured as designed. It tells you nothing about whether the design is correct functionally. Indeed, this would be a very expensive time to discover a design bug. The assurance that the chip is designed correctly comes from the various verification steps that preceded release of the gate-level netlist. As it verifies the translation from gate-level netlist to silicon, manufacturing test does two things. First, we do not want to ship defective chips. However, this would not be engineering if there were not a trade-off. So we must balance based on our understanding of customer requirements, minimizing the number of bad chips we ship, called escapes, while also trying to maximize yield. Some kind of defects may not prevent a chip from working functionally. Do we throw it out anyway? Some tests have soft results suggesting that the chip may have problems in the future even though it passes tests now. Do we still ship it? For a wafer, all passing chips except one may be well within tolerance, and one is just barely in. Is it good or bad? Second, the manufacturing tests provide immediate and important feedback to the chip manufacturing line about how well the process is tuned and operating. To bring up a new process or new line, careful and expensive failure analysis attempts to trace as many defects as possible back to their root causes so that the process can be optimized. Sometimes this analysis provides insights to new defect mechanisms in the process or the line that needs to be investigated and changed. So chip manufacturing test is an integral part of the continuous improvement cycle that has enabled the semiconductor industry to follow the Moore's law's exponential growth curve. So what do we look for when we test the chip logic in manufacturing? Defects are errors or glitches or mistakes in the manufacturing process that produce a chip that does not behave exactly the way it's expected to. Defects are presumed to cause incorrect behavior later if not immediately and therefore must be rejected. For example, in the picture on the left there is some extra metal shorting two metal traces. In the picture on the right, a metal trace has become detached from the substrate and buckled. If the buckled trace is not touching the other trace, there may not be a functional error. But do you want to ship it? Will later mechanical vibrations cause it to either short to its neighbor, or might it break off and create an open? There is damage in a line across a number of traces, so there is more going on here than that simplistic analysis would suggest. While we would like to directly test for each and every possible defect, there is in fact no way to directly observe most of them. So we observe their effect on circuit operation and categorize those behaviors. For example, let's pretend that the short in the picture is shorting the transistor gate metal, which is shown in red in the drawing of a 2-transistor inverter, to the power supply ground trace, which is the cyan trace across the bottom. The transistor gates are the input of the inverter, so this defect would cause the input of the inverter to be stuck at ground or 0, and the output to be stuck at 1. This stuck-at behavior can be observed digitally using the circuits of the chip itself. Thus, rather than testing directly for defects, a short in this case, we test for the observable digital and sometimes analog behavior that the defects cause. In this manner, many different kinds of defects which cannot be directly observed are abstracted into a smaller set of behaviors that can be directly observed. So while it is impossible to know, a priori, all of the possible defects that could occur on a chip, much less observe them, we can observe the specific incorrect behavior that would be caused by the defects. We call these observable behaviors faults, and the set of such behaviors we test for a fault model. The most commonly used fault model is a stuck-at model we have just illustrated. Based on many years of use, it does a very good job of detecting defects that cause static, which are non-time varying incorrect behavior. This would include hard shorts and opens in the various metal traces, for example. In recent years, newer technologies have been exhibiting time-varying behavior due to defects, and these behaviors are described by the transition fault model, which observes when a pin is too slow when it changes state. This will occur when a short or open is resistive rather than hard. Tests commonly used in technology nodes above 16 nanometers that observe analog behaviors include the IDDQ test that observes supply current changes while stuck faults are stimulated, an I/O parametric test that observes whether the I/O drivers and receivers meet their analog current and voltage specifications. In smaller geometries, 16 nanometers and less, it is becoming more common to test for faults inside the standard cell models themselves. One common model is called cell-aware. As mentioned earlier, the most common fault model by far is the stuck-at fault model. This has been in use since the early 1970s and has proven very effective at detecting most manufacturing defects that affect static logic operations. In this model, it's assumed that a defect will cause the pin of a gate to behave as if it is stuck at a specific logic value, a 0 or a 1, and sometimes X. The defect could, in fact, be in the transistor itself or on the traces connecting to the gate. The stuck-at fault model is also referred to as static faults because the behavior does not vary with time. These days, most companies are pushing to achieve 99% stuck-at fault coverage. For example, in this diagram of an inverter, we assume that due to a manufacturing process problem, not all of the metal shown in red is etched away properly, leaving an excess of metal at the bottom of the shape that would be the transistor gate. This excess of metal overlays the location of the via from the ground power distribution trace to the drain of the transistor, so the gate will be shorted to ground when the via is etched and filled. This excess metal is the defect. Its fault behavior is the gate input stuck at 0, or equivalently, the gate output stuck at 1 for the static logic tests. Note that the short may also create other abnormal behaviors. In IDDQ testing, an attempt to drive the input to this inverter high will cause excess current. There may be other abnormal behaviors in other test modes. A fault model that has been around for a while but is coming into greater use as we move to smaller and smaller transistor dimensions is the transition fault model. In this model, defects such as resistive shorts and opens are abstracted to their behavior. The signal toggles but does so too slowly. The faults are called slow to rise and slow to fall faults, and sometimes collectively referred to as dynamic faults since the behavior is time varying. Obviously, to test for these faults or behaviors, a transition must be generated that propagates through the pin that the fault is defined for. In the sense that a stuck-at value is just an extreme of a slow-to-rise value, this fault model is a superset of the stuck-at fault model. For example, in this inverter layout diagram, again, a process problem has prevented the via from the input of the red gate-level metal from being properly filled. Some metal was deposited, but the via exhibits many ohms of resistance instead of its nominal fraction of an ohm. Since the gates of the two transistors have a significant amount of capacitance, the RC time constant of the input is now much slower than expected, and the signal will not toggle with its expected transition time. It could easily be a couple of orders of magnitude slower than the expected transition time and will prevent the chip from operating in its functional mode. Note that this exact problem is why most modern technologies use redundant vias. These defects passed stuck-at tests but failed transition fault tests. Diagnosis and failure analysis revealed the root cause, and the mask generation software was changed to create redundant vias. This is an example of using test results to help refine the technologies and the manufacturing process. Here are some examples of defects that cause transition fault behavior. First, in the upper photograph, you can see that there is an apparent gap in one of the horizontal traces, yet this passes static tests. When the chip is sliced through the gap, shown in the lower photograph, you can see that there is a thin conductive layer that creates a resistive open. This defect causes the input driven by this net to exhibit a slow transition, but not very slow. Here is another example. You can faintly see a faint streak across the face of the chip. This is some form of contamination of the silicon, and it creates a resistive short across several nodes. Again, the part passes static tests. This additional load on the nets causes a slow transition at one or more inputs. These two examples come from a discussion of difficult-to-test defects. Most defects that cause transition fault behavior will be worse than these two. Most defects that cause transition fault behavior will be worse than these two examples. It's time now for a pop quiz. Now that we know why we test and we have a feel for what we're looking for, how do we actually generate the tests? Any kind of testing is always a matter of controlling the device that's being tested and observing its behavior. In the case of an SoC, we can only control the chips through the input pins and observe it through the output pins. We cannot directly access internal nodes to control or observe their states. For each fault, we need to manipulate the inputs to establish a circuit state that is both sensitive to the presence of the fault and will propagate the response to an observation point. Sensitive to the fault means that the circuit will produce different responses depending on whether the fault is present or not. We then compare the observed response to the predicted value. For a modern chip, there are millions and millions of faults, so it can take a long time to compute all these tests, and can produce a very high volume of data and take a long time to apply. Over the years, many simplifications have been adopted to reduce computation time, test data volume, and test time in manufacturing, and we'll look at a few of these cases. Most, however, are buried deeply in computational algorithms and do not change the basics of test generation, so we will ignore them. If you are already familiar with test and concepts such as scan, some of these slides may be review. We're going to be starting from the beginning with functional test patterns. Originally, some subset of the chip verification patterns were used to verify that the chips had been properly manufactured. This makes a lot of sense. If the simulations are sufficient to ensure that the design is correct, then they should also ensure that the chip was manufactured correctly. Unfortunately, that is not sufficient. There's still no generally accepted means for determining the completeness of functional verification. The advent in the early 70s of the stuck-at-fault model and fault simulation, also called fault grading, found that functional verification patterns provided poor coverage at best. Furthermore, as chips got larger, the controllability and observability of logic states within the chip became harder, and more effort was required to create the functional patterns. It's not unusual, even with reuse, to see as much human resource used to generate functional test patterns as is used to design and verify the chip. Finally, it's extremely difficult to determine the root cause of a failing functional pattern. Still, functional patterns are used as a supplement to automatically generated patterns. It's a well-known fact in the test industry that if you can afford to do it, every additional type of test you can throw at the chips will detect a few defects that are otherwise not detected. Today, however, that usually means adding more automatically generated tests. In order to achieve a nearly complete test of a chip, a simplifying assumption was made. The function would be ignored and tests would be generated that verified that the behavior of the silicon matched the gate level netlist. This is called structural testing. The list of faults is generated gate by gate. Picking one fault and generating a test pattern for that one fault required that signals be traced through the gate level netlist to determine where to apply what values to chip inputs. Thus the patterns test the chip gate by gate and interconnection by interconnection, rather than testing functions per se. In addition, the pattern generator only needs to understand the function of a small set of primitive logic functions, for example ands, ors, etc., and not the function of the circuit as a whole. Thus, it can be automated. All modern test tools use structural testing for ATPG or automatic test pattern generation. This is a basic structural ATPG loop. A single fault is randomly selected from the consolidated fault model. The test generator attempts to generate a test for that fault. If unsuccessful, the fault is marked as untestable and another fault is selected. If a pattern is successfully generated, it's passed to the compaction program. This program merges tests that are compatible, which means that they have the same clocking sequence, which we have not introduced yet, and no conflicting values on any input, into single patterns. Eventually, the compaction program determines that some set of a pattern is as full as they're going to get, and passes them to the fault simulation program. The unspecified bits of each pattern are filled, usually with random data, and then the netlist is fault simulated with this pattern. First, the pattern is simulated with no faults applied to the netlist, and the results are recorded. Then the netlist is resimulated with each undetected fault one at a time. The result of each of the simulations is compared to the results with no faults, and if there's a difference, that fault is marked as detected. Finally, the pattern is appended to the set of simulated test vectors if it detected at least one fault. So how do we generate that test for a single fault? As mentioned before, a single fault is selected, usually at random. The cell pin with a fault is set to a value opposite of that fault. For example, a 1 if the fault is a stuck-at-0 fault. Then the back cone from this pin is traced in order to determine a set of primary input values that will force this value. The other cell pins are set to non-controlling values, so a cell output will be different depending on whether the fault is there or not. The back cones for these values are traced to determine the additional primary input values needed to force these values. Then the forward cone from the cell output that is affected by this fault is traced to find a primary output that can observe the value. The back cone from the primary output is then traced to determine what additional primary input values need to be set to sensitize the path from the cell output to the chip primary output. Note that for a dynamic fault, the test must also specify a specific transition, 0 to 1 or 1 to 0, on one of the primary inputs. If all that cone tracing fails to find a set of primary input values that sensitize the fault and propagate its results to a primary output, then the fault is marked as untestable. In a well-designed circuit, this should not happen very often. Here we have an AND gate that we assume is embedded in the middle of a combinational design. The fault selected is a stuck at 1 on the first pin of the AND gate. Stuck at faults are often shown on diagrams as shorts with vertical arrows. According to our algorithm, the pin with the fault must be set to a value that is opposite to the stuck value, namely a 0. The back cone from the AND gate input is traced, and a set of values are determined that will force that pin to 0. This is called justifying the 0 value on that pin. The other input pin of the AND gate must be set to a non-controlling value, namely a 1. The back cone from the AND gate input is traced, and a set of values are determined that will force the pin to 1. We now know that the output of the AND gate will be a 0 if there is no fault present, and a 1 if there is. This is normally represented as a 0/1 value on the pin. The forward cone from the AND gate output is traced to verify that the AND gate output value can propagate to one or more primary outputs. The back cone from one of the primary outputs is traced, and a set of values are determined that will sensitize the path from the AND gate output to the primary output. This is referred to as propagating a fault effect. This pattern is just one of many that might test this fault. Cone tracing works best in a purely combinatorial circuit. It's your turn to try to sensitize this fault. Here is a portion of a circuit. The inputs and outputs could be scan flops or primary I/O. It doesn't make a difference in this case. The first step, of course, is to sensitize the fault. What values have to be placed on the inputs of the AND gate with the fault? Did you get the right values? Now define a set of inputs and the resulting values on the logic feeding the faulty gate that will result in the correct sensitization values at the input to the faulty AND gate. There's more than one correct answer here. Here is just one possible solution for the test values on the faulty AND gate. On the upper AND gate input with a fault, the required value of 0 means that both inputs of the OR gate must be 0, which also means that at least one input of each of the AND to the OR gate must be 0. On the other input to the faulty gate, the 1 value requires that one of the OR gate inputs be 1, and we chose the AND gate input to the OR with the fewest inputs since all of the AND gate inputs must be 1. Note that not all of the input values are specified. Now, what is a good machine fault machine value on the faulty gate output, and what input values will propagate it to an output pin? Given the values chosen to sensitize the fault, the upper path could not be used to propagate the fault value to an observation point. The lower path could be used, and 2 additional input values were added to sensitize the propagation path. We now have a complete test cube for this fault. Unfortunately, we don't build purely combinatorial chips very often. So how do we have to change the test generation for single fault if there are registers in the design that control those cones we are attempting to trace? This situation is the norm. When backtracing runs into a register, then the test generator must set up another set of bits to cause the desired value to be captured in the register when the register is clocked. This must be done recursively until the chip's primary inputs are reached. All of these must be applied in sequence prior to testing the fault. Similarly, when forward tracing from the output of the gate, additional patterns and clocks must be applied to capture the observation in a register and then to move it recursively through registers until it can be observed at a primary output. All these additional patterns must be applied after testing the fault. This results in a test for a single fault having multiple patterns and clocks. This makes it very difficult to compact tests for multiple faults. Alternatively, the test generator could retain the state of all internal registers and use that as a starting point when tracing. This makes all of the final test patterns dependent on each other, which is not desirable. To illustrate this, let's add only a single register in one of the backtrace cones. We again apply the stuck at 1 fault to the first pin of the AND and set the pin to the opposite value, 0, and backtrace. We now have assigned required values to a couple of primary inputs and to the output of a flip-flop. To get that value on the output of the flip-flop, we need to set other values on the inputs of the flip-flop. Plus indicates a positive pulse applied after the other inputs are applied. Backtracing from these values, we get another set of primary inputs, but these must be applied prior to the other inputs controlling the AND gate pin. They are a separate pattern. Again, we apply the non-controlling value to the other AND gate input pin and backtrace. We determine the observable fault effect, trace it forward to possible observation outputs, and trace one of those back. We now have two patterns that must be applied sequentially. In a realistic case, we would have an indeterminate number. Application of a single fault test might require moving a finite state machine or a counter from an unknown state to a known, desired state. This can take many patterns and clocks. So how are we going to resolve this? The way to eliminate the sequential nature of the circuit is something called scan test. All flip-flops in the circuit are modified so that they have two data ports. They are then connected so that in scan mode, one data port is used to form all flip-flops into a set of shift registers between a set of primary inputs and a set of primary outputs. By setting the chip to this scan mode, the internal state of the chip can be controlled from the scan-in pins to any arbitrary logic state with a single scan load. In addition, the previous internal state of the chip can be observed at the scan-out pins with a single scan unload. In effect, for test purposes, every flip-flop acts like a chip's primary input and primary output. That is, after scan, each flop is a control point holding an arbitrary value that can be assigned by the test pattern generator. Then only the application of a clock is necessary for it to observe the test results at each storage element, which can then be scanned out. Using the flip-flops in this way leaves only the combinatorial logic to be tested, which we know how to do. The cost is at minimal increase in the area of each flip-flop and some increase in wiring congestion, both of which are taken into account in modern technologies. Scan is a fundamental concept enabling ATPG. It is at the core of almost all automated test processes, including scan test for chip manufacturing, the IEEE 1149 family of board test standards, logic BIST, and test compression. All depend on a scan mode for test control and observation. How do we create the scan mode? First, all flip-flops in the design must be converted to an equivalent that has selectable input data ports. One of these ports is used for functional operation and the other for scan operation. There will normally be a test control signal that switches the circuit between the scan state and the normal functional state, called scan enable by convention. For the traditional flip-flop, which captures its input on the rising edge of its clock, the simplest way to do this is just add a 2x1 multiplexer on the data input of the flip-flop. The multiplexer is controlled by the scan-enabled test control signal and selects either the functional data input or the scan data input. The differentiation between the functional data input and the scan data input is a matter of convention. Here we show in red the additional connections required when converting a conventional flip-flop design to a scannable design. The scan input of each scan flip-flop will be connected to the output of one other scan flip-flop or to a scan-in chip test input. The output of each scan flip-flop will, in addition to its functional connections, be connected to one other scan flip-flop or to a scan-out chip test output. This forms one or more scan chains. The scan-enabled test control signal must be wired to every scan flip-flop. The clock is not modified for test but must be able to be controlled from the tester. There are other architectures for converting flip-flops and latches to a scan element, but the basics remain the same. The ATPG program treats each scanned flip-flop as both a primary input, meaning that the ATPG can set each flip-flop to an arbitrary value, and as a primary output, meaning that the ATPG can observe any value captured in each flip-flop. All that is left to test is the combinatorial logic shown as a blue cloud. Let's take a look at how this is done, loading the stimulus, capturing the circuit response, and unloading the responses. Here we show just the logic in the design needed to load the scan chains with control values. The scan-enabled pin is set to the scan value. Then the stimulus data, calculated by the ATPG program, is supplied serially at the scan-in pin 1 bit per clock pulse. The clock is pulsed the same number of times as the length of the scan chain. At the completion of this operation, new stimulus data will have been loaded in each and every scan flip-flop. Then the scan-enabled test control input is set to the functional operation state, and all functional primary inputs are stimulated. All of the control values specified by the ATPG algorithms are now in place. The clock is pulsed as specified by the ATPG programs. This exercises the logic and captures the values that result into the flip-flops. All functional primary outputs are observed, but the values captured in the flip-flops have not yet been observed. All functional primary outputs are observed, but the values captured in the flip-flops have not yet been observed. To unload the captured responses, the scan-enabled pin is again set to the scan state. The clock is pulsed the same number of times as the longest scan chain, and the results are captured into the flip-flops and are observed at the scan-out pin, 1 value per clock pulse. In reality, the loading of the stimulus for the test can be done at the same time as the unloading of the captured responses of the previous test. This is referred to as overlapped scan and is a normal way of applying and observing scan tests. To use scan, we have to give the test pattern generator the correct control and clocking sequences at the chip primary inputs to perform a scan. It then generates a few patterns to verify that the scan chains themselves work. These few patterns will actually pick up several percent of the total faults in a typical chip. One of the simplifications used to reduce the test generation computation time is that after these first few patterns, the actual scan is never simulated. The desired control values are loaded directly into the scan flops, and the values captured in the scan flops are directly observed by the fault simulator. We can now proceed with the ATPG loop we discussed earlier for the combinatorial logic tests, with the addition that the test generator must set test control primary inputs and pulse the clocks as required to launch the scan data and launch transitions for dynamic tests and to capture the design response into the observing flops. While the discussion has assumed full scan, which is that all flops are in the scan chains, the combinatorial test generator will tolerate a small number of non-scan flops, particularly if there is no feedback around the non-scanned flops. The more non-scanned flops in the design, the higher the computational time and number of test patterns it may take to achieve the desired fault coverage. In addition, when there are larger numbers of non-scanned flops, sequential test pattern generation may be used to supplement or even replace combinatorial test generation. At this point, we've covered how the tests for each fault are generated and the role that scan plays in making that happen. The next step is to compact all these individual tests into a smaller number of test patterns. Tests for single faults may be merged if they do not have conflicting values applied to the same primary input, and if the launch and capture clock and control sequence is the same. The scan sequence is always the same by construction. The compaction program maintains buckets of patterns with compatible clocking and keeps track of how often a new test is merged into a particular pattern. Based on user selectable criteria, the program will decide when it appears that no more tests are merging into a pattern. The remaining unspecified bits of the scan load are filled, usually with random data. The pattern is then passed to the fault simulator. In the fault simulator, the good machine response, when no faults are applied, is compared to the response of the circuit with each untested fault applied one at a time. When the responses differ, the fault is marked as detected. For an average pattern of a large chip, the density of the specified bits will be less than 2%. There will be a few patterns in the set that have specified bit densities in the 20% to 90% range, and many that have densities well below 1%. The first few patterns will have very high density and test many faults. Here we show the values to be loaded for a single pattern into 3 scan chains in a chip that's being tested. The test generator creates a test for fault 1 with just a few bits specified, and this is passed to the compaction program. Perhaps this is the first test cube, as tests for single faults are called. Let's say this test cube doesn't fit in any existing vector. So the compactions program creates a new vector that initially contains just this one test cube. Tests for additional faults specify additional bits as they are merged. Note that the different tests may share some specified bits. After some time with no additional tests merging into this pattern, it will be filled and sent to the fault simulator. Note that most of the data that will be scanned into the chip is fill, usually pseudo-random data. This low density of specified bits has 2 important consequences. 1. Most of the test data is fill, and many of the faults that will be detected in the fault simulator will be detected by this fill data, especially pseudo-random fill. This happens because the fill accidentally sensitizes and propagates a fault effect. The low density of specified bits allows us to compress the test patterns. The patterns will be decompressed and filled by on-chip logic. Compression is actually performed as a part of the compaction of the individual tests, and details are covered elsewhere. However, compressed test patterns may have average specified bit densities in the 20% to 80% range, instead of the 1 to 2% range. Detection of faults is not a linear process in terms of the number of test patterns versus coverage. As shown, coverage, which is the percent of faults detected, starts with the results of the test of scan chain operation and grows rapidly at first, but it quickly rolls over as the easy-to-detect faults are all detected. Then coverage grows slowly until all testable faults have been detected. Most of the patterns are in what's often called the tail of the curve, the area where coverage grows slowly. There is an engineering trade-off here, where drastically reducing the number of test patterns, and therefore the cost of test, also reduces the coverage, but only a little. But system cost can build up rapidly, especially in complex systems due to test escapes. The length and slope of the tail are heavily affected by a number of factors. One that is under the control of the chip design team is how well they have followed the design rules. Compliance with the design rules will often have significant impact on chip quality, manufacturing test cost, system test cost, field returns, and customer satisfaction. It's time now to take this pop quiz. There are 2 categories of design rules: those that affect the ability to test certain faults or that affect test coverage and time, and those that are required for the proper operation of the scan chains, shown here. If these rules are violated, the scan chains will not operate properly and the chip cannot be tested, so exceptions are rare. First, all test control and clock inputs must come from chip primary inputs, and all clocks used in the logic design must be controlled by chip primary input, at least during the scan mode. A clock is any signal that, if pulsed by itself, can change the state of a storage element. So during scan, the clocks that affect scan cannot be gated off. Derived scan clocks, asynchronous set and clear signals, and free-running clocks must be overridden by clocks controlled from tester primary inputs. Normally, these changes are affected by test control called scan enable. This is a minimum needed to ensure that scan will work at all. Scan chain must originate at a chip input and terminate at a chip output. The chains may not be broken. This ensures that the state of all internal storage elements may be controlled and observed. In an environment where multiple clock domains exist, and flip-flops may be clocked by either edge of the clock, retiming latches and scan chain ordering must be used to ensure that the scan will work robustly. Changing any of the chip test control inputs may not cause the state of storage elements to change. This ensures the integrity of the scan data. This is why asynchronous set and clear signals cannot just be de-gated by scan enable. Finally, for Mux-Scan type designs, the delay from scan element to scan element in a chain must exceed the sum of the worst case clock skew plus the scan element hold time. This ensures that the data will propagate properly through the scan chains. Where this cannot be guaranteed, retiming latches are added to the scan paths to provide controlled timing. These are typical of the rules that are required to ensure operation of the scan chains, without which the chip cannot be tested. Of the rules that affect test time, data volume, and cost, some are higher priority than others since they may in certain cases cause the test generator to generate invalid test patterns. Strong structure verification rules checking will detect almost all structural or non-timing rules violations. In certain situations, the user may choose to ignore the violation, but should ensure that the condition will not, in fact, create bad patterns. Otherwise, time to market will be adversely affected by first silicon debug of patterns, something we believe should not be necessary. First among these design rules is no combinational feedback. In effect, combinational feedback creates unclocked memory in the circuit. Its state is not determined slowly by the circuit input. This effect is not modeled in the test generator, which assumes that all of the combinational logic starts at an unknown state for each test pattern. If logic cannot be modeled as gates, it cannot be understood by the test generator. IP that's provided as a black box with test patterns are acceptable. Clocks may not be used as data inputs to flip-flops. The timing of clock pulses is different from the timings of data inputs. Finally, if there are any paths that are slower than the intended tester cycle time, the test generator typically cannot recognize the situation and determine the correct capture value. The remaining rules only affect test coverage and cost. The first is that there be no three-state or other multiply driven nets, including transmission gate, one-hot logic. If the logic guarantees one and only one enable will be active at a time, this rule may be violated without problems. Test structure verification can check for such mutually exclusive control, or correlation information can be added to prevent the test generator from creating patterns with orthogonal drive after the end of the scan. There should be no visible X state generators in the logic. While the test generator will simply record the X state in the responses, a chronic X state generator will block the testing of some faults. Non-scan storage elements, including memories, are assumed to contain X at the end of scan. Thus, they violate this rule and generally make it difficult or impossible to test many faults. For memories and other X-state generators, the situation can be corrected by designing a wrapper that observes all inputs and controls all outputs, fully isolating the generator from the rest of the logic. The chip must be scanned for the longest chain. Unequal scan chain lengths waste space in the scan buffers for the shorter chains and take longer to perform the scan. With modern tools, scan chains should be balanced within a few percent. One topic that often comes up when discussing scan ATPG is the debate about the two basic scan styles, LSSD and Mux-Scan. As with many debates, there is less to this one than meets the eye. Most foundries accept either, and the two styles can and have been intermixed in a single chip. Basically, in order to scan data in a stable manner, each storage element is actually made up of two latches, usually called the master and slave latches. Data is loaded into the master latch while the slave is held stable. Then the data is moved to the slave while the master is held stable. In level-sensitive scan design, or LSSD, separate test clocks are used for the master and slave. These are pulsed with plenty of off time between them, guaranteeing stable operation. In Mux-Scan flip-flops, the master and slave are clocked with opposite phases of the same clock. There's virtually no off time in this scenario, meaning that the timing has to be checked carefully to ensure that the scan works properly. The LSSD rules are clearly defined and strict, in part because it was developed when ATPG was brand new and not as powerful as today's ATPG. It has the nominal advantage of being totally insensitive to timing issues and the disadvantage of requiring multiple test clocks. Mux-Scan today depends on timing tools to verify proper scan operation. The Mux-Scan design rules are more loosely defined and there is little agreement about many of them. It's time now to take this pop quiz. Now we'll take a quick look at some of the other test methods, starting with built-in self-test or BIST. In general, BIST simply means that the test stimuli is generated on chip. The responses are captured on chip and the test itself is controlled on chip. The stimuli may be deterministic or pseudo-random and the responses are normally compressed to a pass-fail value, which is checked at the end of the test. Otherwise, all of the concepts and rules discussed before still apply. There's a lot of appeal to the idea of a chip testing itself. The test can be used not only for chip manufacturing, but for board, system, and even field testing of the chip. We see BIST used in automotive components for in-system or at the time the car is turned on. The trade-off is the silicon area consumed by the BIST circuits and the coverage achievable with on-chip stimuli generation. There are variations that give the tester more or less control. The onboard controller may need nothing more than a clock and a go test signal, or the tester may have to program the test first, or the tester may actually provide the entire control function, possibly on an override basis. Testing of large, very regular structures, particularly memories like SRAMs and DRAMs, is one area where BIST shines. The deterministic patterns in terms of address, data in, and data out needed to fully test RAMs are well understood and reasonably easy to implement in silicon. As a result, virtually all RAMs instantiated in chips today have a memory BIST controller built into or instantiated within the memory. Some of the RAMs are designed with extra rows or columns of memory cells so that when a defect is discovered, the defective memory cells may be switched out and the extra memory cells switched into their place. The MBIST will provide the row or column information or failing bitmap to support this. ROMs, while regular structures, are normally just checked with a simple checksum of the contents. Logic BIST is also popular for some applications. Logic circuits are so varied that the test stimuli is just pseudo-random patterns, usually generated by a pseudo-random pattern generator, PRPG, normally a form of a linear feedback shift register. The responses are compressed using a multiple input signature register, usually another form of an LFSR or a linear feedback shift register. The controller consists of a state machine and a few counters. On a typical large chip, these extra circuits will take up less than 1% of the silicon area. To hold down test time, Logic BIST is normally implemented with many more shorter scan chains than a typical ATPG test structure. The primary use of Logic BIST is for board, system, and field testing. The disadvantage of Logic BIST is that the maximum coverage it provides usually is significantly less than testing with deterministic ATPG patterns. Random fill data used in ATPG patterns detects a lot of faults but not many of the hard-to-detect faults. It's the same situation here. Testability may be improved if test points are inserted in the logic, but that takes extra design time late in the release cycle. Because a signature register is being used to capture the responses and compress them to a pass-fail value, the capture of an X state would destroy the signature value and is therefore not allowed at all. Another common methodology for reducing test time is test compression. This is motivated by the fact that for large chips, the test data volume has become too high to fit on many testers, and the test time has driven test cost up to where it almost equals the cost of manufacturing the chip. The test structures used by most compression schemes look remarkably similar to Logic BIST, with the biggest difference being that the generation of the stimuli is controlled by the tester. This preserves the very high coverage expected during chip manufacturing test. ATPG generates the tests for each fault as normal, and the compaction program creates the compressed test patterns. Fault simulation simulates the decompression circuits, marks off detected faults, and adds the compressed response data. The goal of test compression is to reduce the data volume and test time to a few percent of the original without compression. The ability to compress test data depends on all these unspecified bits in the typical ATPG test patterns. By adding logic on the chip that decompresses the test data with a known algorithm, then the single fault tests can be merged using the inverse algorithm to create a much smaller set of test patterns. This depends on the compression and decompression algorithm being linear and reversible. The decompression could be combinatorial, but most algorithms assume a linear sequential circuit very similar to the PRPG used for logic BIST. Compaction is the process of merging single fault tests and traditionally assumes no decompression on the chip. That is, there's one bit in the vector for each scanned cell. Compression assumes a specific decompression circuit on the chip and packs the specified bits for the single test faults into a much smaller data structure. Test time is dependent on both the data volume and the length of the longest scan chain on the chip. For normal ATPG, the length of the scan chains is set by the memory behind the pins on the tester, as well as the design's pin limitations. Since the decompression of test data is done on chip, many more scan chains, correspondingly shorter, can be used. So savings in test time are realized by increasing the number and decreasing the length of the scan chains. For diagnosing failures, there is normally a traditional scan mode built into the chip to allow the uncompressed responses to be recovered. This supports the full diagnostic capability. In addition to static and dynamic tests that we've been discussing, there are other types of tests that must be generated in order to complete the manufacturing test of the chip. The common ones are IDTQ tests, which measure supply current as the faults are stimulated, I/O wrap tests used to test uncontacted drivers and receivers at wafer test, and I/O parametric tests used to verify that drivers and receivers meet their analog specifications for voltage and current during module test. It's time now to take this pop quiz. After all that, the patterns are all packaged together and meet the chips and modules at one of these testers. The chip or module sits in the middle of the test head, hanging outside the rack of electronics. The result is that some modules will fail and some will pass. For some number of chips that are tested, some will fail test and be rejected, and the others will pass and will be shipped. But tests are not perfect, so some of the chips that pass test will in fact be defective and will not work correctly in the system. These parts are called test escapes. Obviously, we want to make this group as small as possible. So how good are the test patterns? How do we measure the quality of the test results? The normal measure of test quality is the fault coverage. This is simply the percentage of faults that are tested. But what does this really tell us? If the calculated fault coverage is 99%, does this imply that 1% of defects will not be detected and 1% of the passed chips will be defective? Not necessarily. Many defects will cause multiple fault behaviors and may affect multiple nets or transistors. This means that the defect may be detected even if some of the possible incorrect behaviors or faults are observed. As a result, the percentage of escapes is typically less than the percentage of untested faults, but the exact ratio is not typically known. The chart shown on a log scale is for a particular mature bipolar technology and illustrates the fact that the percentage of escapes is less than the untested fault coverage. For this technology, it is lower by a factor of 5 to 10. So is high fault coverage not important? Not necessarily. Escapes result in incorrect behavior at the board, system, or field level depending on when it is detected. Defective behavior at these points will cost significantly more than just the cost of the chips themselves. The impact of escapes depends on both the complexity and the quality requirements of the system. It should make sense that a high percentage of escapes will have less impact on a low-cost consumer product with only a few chips than on a complex, expensive system containing many chips. In this plot, we take the escape percentage for 3 different fault coverage values from the previous chart and calculate the percentage of defective systems that would result just from bad chips. Plotting this against the number of chips, we get the lines that are shown. Clearly, for this technology, chips intended for complex systems with high quality requirements may need to be tested to better than 99% fault coverage, despite the very low percentage of escapes implied. Chips intended for simpler systems with lower quality requirements may be able to get away with fault coverage in the mid to high 90s. The ultimate trade-off is the cost of building the systems, including the cost of manufacturing chips and the cost of repairing defective systems. Like all engineering trade-offs, there's not just one correct answer. Finally, once we start getting failing chips, we want to know why they failed. So what can we do? Each miscompare contains the information, which scan chain, which scan cycle, to uniquely identify the flip-flop that captured the incorrect value. Simulation and tracing algorithms use this information to generate a list of possible causes called a call-out list. The test pattern generator can generate patterns to differentiate between the possible faults. Once the most probable logic faults are called out, they may be mapped onto an image of the chip, mapping the fault information from the logical to the physical domains. This provides a starting point or points for the failure analysis team to start investigating. Optical inspection of the identified area is a frequent first step, as many defects of the wiring will be visible. If analysis tools such as electron beam or picosecond imaging circuit analysis are to be used, the test generator will create a small set of patterns that will continuously re-stimulate the suspected fault in a tight loop. This will allow these tools to build up an image of the behavior over many repetitions. It can be very valuable to monitor the types of defects that are occurring. This can identify weaknesses in the design of the technology cells and act as the ultimate monitor of the technology process and manufacturing line. If the defects are dominated by one type of defect, for instance, it is probable that the process can be adjusted to eliminate most of that defect. This is how the yield of a technology process is improved over time, holding down the cost of chips and enabling Moore's law, as well as helping us sort out good chips versus bad chips. Here is an AND gate, and we'll assume that the defect is causing its one input to behave as a stuck-at-one fault. But we don't know that yet. All we know is that we have some miscompares in a specific pattern. First, we apply the failing test pattern stimuli to the circuit. The simulation of the pattern will apply controlling and non-controlling values to input pins throughout the circuit, including the 2 inputs to the AND gate that's shown. The output miscompares are traced back through sensitized logic, creating cones of logic that could have caused each miscompare. Assuming only a single defect, it must be in the common area covered by all the miscompare cones. The non-overlapping areas are pruned from the list of possible faults. Some of the outputs that were correct can also be traced back through sensitized paths. These essentially exclude logic from the area that could create the miscompares, as shown by the 2 outer cones that do not include the AND gate. The process continues, gradually reducing the list of possible faults. If necessary, the test pattern generator can be used to create special patterns that sensitize some of the possible faults and not others. These patterns are applied to the chip and the results are added to the analysis. The actual algorithms are much more sophisticated than this and can handle multiple simultaneous defects, use multiple failing patterns, and so on. Specifically, if you assume that there could be multiple defects, then all of the faults in any failing cone must be considered, not just the overlaps of the cones. The list of possible faults is prioritized using fault simulation of the candidates, but this should give you the gist of how the process might be performed. Some of the outputs that were correct can also be traced back through sensitized paths. These essentially exclude logic from the area that could create the miscompares as shown by the two outer cones that do not include the AND gate. The process continues, gradually reducing the list of possible faults. If necessary, the test pattern generator can be used to create special patterns that sensitize some of the possible faults and not others. These patterns are applied to the chip and results are added to the analysis. The actual algorithms are much more sophisticated than this and can handle multiple simultaneous defects, use multiple failing patterns, and so on. Specifically, if you assume that there could be multiple defects, then all of the faults in any failing cone must be considered, not just the overlaps of the cones. The list of possible faults is prioritized using fault simulation of the candidates, but this should give you the gist of how the process might be performed.